Hello everyone. This is the sixth video in the series of lectures on linear algebra. So in this video, I'll explain about basis and dimension of a vector space. Let's see what is basis of a vector space. A non-empty set P of vectors v1, v2, so on up to vn of a vector space V over F is said to be a basis if the first condition is B is linearly independent and the second condition is span of B equal to V. In that, if these two conditions are satisfied, then we call that set B as a basis of a vector space V over F. So I had already explained you what is meant by linearly independent vectors and what is meant by linear span. If you have not watched those videos, please go into the linear algebra playlist of my channel and go through those videos because those videos are basics to understand the concepts of basis and dimension of a vector space. So let us see one by one with the examples how a set becomes a basis of a given vector space. I will take the vector space R square over the field of reals. I'll give you the set P with the two vectors 1, 0 and 0, 1. You know very well that these two are basic vectors. They are representing unit vectors. They are the unit vectors in the direction of x-axis and another is in the direction of y-axis. First we have to check, is this set linearly independent? You know that any two vectors in R square are linearly dependent if one is a multiple of another. That's not happening here anyway. So you can clearly conclude B is linearly independent, or these two are in different directions, so they are linearly independent. Or else, if you want it mathematically, then alpha into 1, 0, beta into 0, 1 equal to 0. This linear relation you equate it to 0. And if you get both alpha and beta as 0, then it is linearly independent. This is giving you alpha comma beta equal to 0. That can be written as 0, 0. Hence, alpha equal to 0, beta equal to 0. Now, the second condition is linear span of these two vectors. So, the linear span of these two vectors is represented here, where alpha beta belongs to R. So that's equal to set of all ordered pairs of the form alpha comma beta, where alpha beta belongs to R. So this is nothing but the entire plane R square. Instead of x comma y, we have alpha beta. Both are scalars here, means they are taken from the reals. Hence, this represents a point in the plane R square. That means it represents the entire plane R square. These two vectors span the entire plane R square. You can write any vector as a multiple of, as a linear combination of these two vectors. Hence, linear span becomes equal to R square. Both the conditions of a basis are satisfied for this set B. Hence, B is a basis of R square. So, this basis in particular, it is called as standard basis, even A2. These are the standard vectors 1, 0, 0, 1. They form the basis of the given vector space R square. That basis is called as standard basis. You can have a number of bases for the given vector space. Now, see here. If I give you a set with two vectors 1, 2, 1, 1, this also forms a basis because this set is linearly independent because none of the vector is a multiple of other. Second condition is that clearly linear span of these two vectors is nothing but the entire plane R square. That is because if you have a set of two linearly independent vectors of R square, then it always spans the given vector space R square. So, or else you can write it like this plus a beta into 1, 1, then alpha plus beta, comma 2 alpha plus beta. These are the set of all vectors of this form. So definitely it covers the entire plane R square. Hence it's also basis of the given space R square. Let me give you one more example. Consider the second example. This example, I am giving you the set with three vectors over R cube. It's a space. Now you have to check, are they linearly independent? So you can get this linear in equation, linear combination equated to 0. Then alpha plus beta plus 2 gamma equal to 0. This first equation, second equation and the third equation. That's alpha plus 2 beta minus gamma. Then alpha with third beta, 3 beta and gamma is equal to 0. When you subtract 1 and 2, you will get this equation. When you subtract 2 and 3, you will get this equation. Hence, gamma comes out to be 0 and beta comes out to be 0, alpha comes out to be 0. If all the scalars are equal to 0, then that set is linearly independent. That is achieved now. Now the second condition is linear span of these vectors. As I told you before, for R square, if two linearly independent vectors you have in a given set, then that always spans R square. Similarly, if you have three linearly independent vectors in a set, then that set always spans the entire space R cube. So you can write the linear combination of these vectors as this, that covers the entire space R cube, hence linear span equal to the R cube. It becomes a basis of the vector space R cube. You can have a standard basis for R cube also, that is 1, 0, 0, E1, 0, 1, 0, E2 and 0, 0, 1, E3. This is called a standard basis of the given vector space R cube. So for any vector space, basis is not unique. You can have any number of bases. But what you have observed is number of elements in a basis is always same. Here this is a basis, this is also a basis. Both sets have 3 elements. So number of elements in a basis is always same for the given vector space. So that gives you the idea of defining dimension of a vector space. Let's see what is meant by a dimension of a vector space. The number of elements in a basis of a vector space is called its dimension, and it is denoted as dimension of that vector space V over F, and we denote it as n. If this n value is finite, we call that vector space as finite dimensional vector space. Otherwise, it is called as infinite dimensional vector space. Let's give an example for a finite and infinite dimensional vector spaces. See, consider this dimension of R square over R is 2. You have seen the standard basis 1, 0, 0, 1. So there are 2 elements in a basis. You have checked with some other basis also. That other basis also contain 2 elements. So dimension of R square over R is 2. Dimension of R cube over R is 3. Dimension of F n over F is always equal to n, where F is some field. So these are all examples for finite dimensional vector spaces. Now for infinite dimensional vector spaces. Take P of x is equal to all polynomials. There is no specification of degree. It contains all possible polynomials. So then that basis becomes 1, x, x square, x cube and so on, because there are all possible polynomials. So now dimension of P of x over the given field is always infinite because it goes on and so on. You may have polynomial of degree 100, polynomial of 1000, 1 lakh, who knows. It contains all the polynomials, so it becomes infinite. So this is an example for infinite dimensional vector space. Now, if you take Pn of x, it is all polynomials of degree less than or equal to n. In this case, the basis becomes 1, x, x square, so on up to x to the power n plus 1. X to the power n, this is, x to the power n, x to the power n. Total number of elements is equal to n plus 1. Because it is all polynomials of degree less than or equal to n, these many elements must be there in the basis. So basis in the sense, if you take any element of Pn of x, you can write that element as a linear combination of these vectors. They will become basis. For example, if you have taken a simple quadratic polynomial x square, then that x square can also be written in the linear combination of these basis vectors as a 0 into 1 plus 0 into x plus 1 into x square, because only x square, rest all 0. Okay, 0 into x to the power again. So any vector, if you have taken, if it can be written uniquely in the linear combination of the given vectors, then those vectors form basis. In other words, of definition of a basis. Hence, dimension of Pn of x is equal to n plus 1. n plus one more element, so n plus 1. It's an example for finite dimensional vector space. See, all are set of polynomials, but here there was a specification of degree less than or equal to n. Here there is no specification, hence this is infinite dimensional, this is finite dimensional. One more example, m 2 by 3. Set of all 2 by 3 matrices. So for this vector space, you know that m comma n is always a vector space over the given field. So B equal to all these elementary matrices will form basis. This set forms a basis of m2 by 3. E1, E2 like that. These are all elementary matrices. So dimension of M 3, 2 is equal to 6. There are 6 elements in a basis. So in general, dimension of M, n is always equal to M into n, because any 2 by 3 matrix, like if you have 1, 2, 3, 1, 0, 5, so that can be written as a linear combination of these matrices. 1 into 1, 0, 0, 0, 0, 0, plus then 2 into 0, 1, 0, rest all 0, 0, 0, 0, plus 3 into 0, 0, 1, 0, 0, 0, plus 1 into 0, 0, 0, 1, 0, 0, plus 0 into 0, 0, 0, 0, 1, 0, plus 5 into 0, 0, 0, 0, 0, 1. So this is how we can write the given matrix as a linear combination of all these elements. Hence, this becomes a basis of the given vector space of 2 by 3 matrices. I hope you understood the concept of base and dimension of a vector space. I will come up with the concept of vectors and matrices. What is the connection between vectors and matrices in the upcoming video. Thank you for watching.